Hello everybody, thank you for joining us today. My name is Ronaldo Pinto and I'm the Global Sales Manager for AFT. Today we'll be talking about exporting forces from Impulse to Caesar. If you have any questions, you can write to me at ronaldopinto.aft.com or you can write in the chat room of GoToMeeting, and we'll have a session of questions and answer at the end of the training. So and I'll try to answer. If not, I'll send you an email responding to any of your questions. So let's start with what can cause Waterhammer. Waterhammer can be caused by many events, including valve closure. It's important to notice that it doesn't have to be a full closure of the valve in order to cause a Waterhammer effect. It can be a partial closure and still originate a Waterhammer. And we'll be seeing an example where we close 90% of the valve and still we have a failure of the pipe. Also, a pump speed change can cause it. A trip or start of a pump, a relief valve crack opening, rapid tank pressurization, periodic pressure or flow conditions like when you have PDP pumps. Waterhammer and forces imbalances. Waterhammer causes transient forces imbalances in piping system. It is very critical and you have to study it. This is a result of fast-moving pressure waves which can change temporary forces imbalance. What happens is the fluid has an inertia, and that energy, when you close a valve, is converted into pressure, and that pressure starts traveling along the pipe. And the thing is, when you have a pair of elbows, on one side you have the static pressure, and on the other side you have the transient pressure, which creates an unbalanced force until the pressure balances in that section of the pipe. So these forces, unbalanced forces, have to be considered as the structural supports because they have to be designed in order to handle these the forces that are going to be submitted to. Waterhammer software. So Waterhammer is a complicated phenomenon, and there are manual method calculations, but the best you can do is use software that is designed to do this type of study, and that is where AFT Impulse, which we'll be using during this seminar, it comes into play. AFT Impulse is a leading Waterhammer software. It was commercially available in 1996, and it has been used thousands of piping system transient, and we have prestigious customers such as NASA, which does the calculations of the Waterhammer using our software. Typically, the issue of primary interest for the engineering analyst is to understand the transient pressure extremes. So when you have when you're using code B31.4, you want to B31.4 is very specific, and it doesn't allow more than 10% above the design pressure. So generally what you do, the concern of the piping, the design in the system, is to that the pipe and the all the components are able to handle this overpressure. So Waterhammers, for calculating Waterhammer, we use AFT Impulse, and this information can be transferred to a pipe stress program to analyze the stresses created by the unbalanced force. This is very useful when you're using B31.3 because B31.3 does not, the code, ANSI B31.3, because the code does not refer to a limit in the surge pressure like B31.4. In the case of B31.4, it has a limit for the stress that that the pipe is submitted to. So let's see an example of how traditionally the calculations of the unbalanced forces is. We have an example here. The flow is having this way, is heading this way in this direction. So we have a pair of elbows identified with node 1 and node 2. And when you close the valve on this side, what happens is, as I said before, the fluid has an inertia that when it's totally blocked, this inertia turns into pressure. This energy turns into a potential energy, and it starts traveling downstream. So when it hits this section of the pipe between node 1 and node 2, we have a high pressure on this side, and we have a low static pressure on this side. So until this pressure is balanced, which happens when this high pressure reaches node 1, we have an unbalanced force that is calculated for the pressure 2, which is the pressure of the of the wave, times the area, and it's positive since it goes in the sense of the flow, minus the pressure 1, which would be the static pressure times the area, is equal to the unbalanced force. So this works best when fully open stops quickly, which means we close the valve completely, as in the example. And to determine the unbalanced pressure, what we have is a dP, which is a rho times C times delta V, where C is the wave speed, also known as celerity. Often is referred to as A, as a synonymous term. Now, complexity of the systems quietly render hand calculations useless when you do have pressure self-steam of inline components change or add or subtract. Like in this example, the pressure can bounce back, so you have a superposition of the pressure. So you would have to consider that into the component. Also, what happens if you partially close the valve and not completely? Another question is, what about the forms of energy of transmission, like friction losses, momentum, area changes? So let's see the system here. Here we have a partial closure of the valve. We have the same node 1 and node 2, but now we have a pressure 3 and an area 3 and a pressure 4 and an area 4. So now we have a set of unbalanced forces that are considered because the valve is closed partially. So now the forces are not so easy to calculate. So we have an equation where we have pressure 1 times area 1 plus pressure 3 times area 3 minus pressure 4 times area 4 plus pressure 2 times area 4. So now we have this equation here, which means the equation is a little bit more complex because we have a component in the middle of this section that creates adds two forces to the equation. So now let's see this example. We have a tank transferring fluid from one to another tank. We have a vertical section, we have a horizontal section, and we have a valve that we're closing, partially closing to 90% in 0.5 seconds. So here we have the graph of how it's closing. We have it closes in 0.5 second, and it doesn't close totally. When the valve is fully closed, the magnitude of the resulting pressure rise of a liquid can be conservatively estimated using the equation, as we said before. The force is rho times C times delta V times A, where rho is the fluid density times the speed of sound times the change of velocity, which would be the velocity in the steady state condition and 0 to 0, and the pipe A would be the pipe area. Without valve closing 90%, one might presume that we can guess as 90% of the rise of the pressure valve, which is rho times C times delta V in magnitude. It turns out that this calculation is incorrect in an order of magnitude as shown in the calculations. So now we see that using this method of calculation and multiply it by 0.9, we would have a resultant force of 150,000 pounds. If we calculate using the proper equation, considering the friction losses and the momentum, the resultant force would be 16,000, which is much, much smaller than the calculated by the hand calculations. So what leaves us? Well, it leaves us that we don't have a ballpark estimation. Our manual method is not reliable anymore. So how can we apply this pressure if we have a partially closed valve area? More certainty. At this point, we know we need we cannot do a manual calculations, and we need a computer-based transient hydraulic analysis to get the pressure data and be able to estimate accurately the forces generated in the system. For simplicity, one might consider neglecting the loads in the valve and just hand calculate the forces in the elbows. As we saw previously, this is not the best estimate because it would give you a high forces that are really over conservative, and you would have to over dimension your supports. So traditionally, for initial final state conditions, the forces should be on zero. That's another thing that we have to consider. Why? Because until, let me go back a minute. Until the pressure comes in here, this does not see the wave. So when it comes here is that when it starts seeing it, so it starts rising in the elbow. So initially it should be zero. If we don't consider the forces and the friction and the momentum, we will the resultant forces that we will get will not be zero. Like here in this case that we're studying, we're closing the valve. Here, as we see, if we don't consider the friction and momentum, we get a yes, we get a non-zero steady state results initially. So this is not realistic. So if we consider the friction and process in the moment, we have this equation. The total force is equal to the difference of pressure and the difference of momentum, which is equal to the difference of momentum times the velocity, which is the momentum. If we use this equation, then we'll get a more realistic results in the equations, where initially it's zero, and then the pressure starts going back and forth. So this is a much more realistic graph of what's happening in this section of the pipe. Let's see comparing the methods. This would be including friction and momentum, and this would be ignoring friction and momentum. So the traditional method would give us 20,000 pounds, and the real method, considering friction, would give us 16,000. So this tells us this is over conservative, and also it's not in the right sense, because here we would have the maximum magnitude in the negative sense, which shows right here 20,000, and the realistic is that it would be in the positive sense, the maximum value of 16,000 pounds. The same would be for the vertical section. This vertical section would give you an estimate of here. Here we have the correct sense, but as you see, it's not zero initially, and we have a maximum, in the traditional, we have a maximum of 3.3, which would be right here, and the frictional momentum, considering friction and momentum, would be 2.9 pounds, which again is less conservative. The use of traditional force and imbalance calculation method can be highly inaccurate. You don't know the magnitude of the loads. As we saw here, we're getting 3.3 and 2.9. Directional of the maximals can be incorrect also. We saw it here. We got a negative sense right here in the force when the real force is in the positive direction, which is in the sense of the flow. And we are ignoring some loads, and that's why we're not getting the same results. It is very important in the method when you calculate, when you have the pressure going under the vapor pressure, you can have vaporization and bubbles, and these bubbles can collapse due to the high pressure. This is a very difficult model using the methods, and hence force calculation under cavitation conditions is not reliable. So we suggest when you're doing the cavitation, if the study, if you see cavitations to calculate the forces, please turn it off, because the bubbles will distort your results, and it will not give you accurate results. So Caesar does three types of analysis, when he does a stress analysis. It's the static equivalent, which we're not going to talk about in this presentation. It does the spectral analysis and the time history analysis. Right now, it's getting to be very popular, time history analysis, because of the capacity of the computers. But spectral analysis is also it can be a useful tool. So we can't discard it per se, because not necessarily it's not a good method to estimate the stresses. So let's talk about the example in detail we're going to work with. As we said, we have tank A and tank B. We're transferring fluid from one to the other. We're closing the valve 90% in 0.5 seconds. So what the fluid is water. The pipe we're using is 20-inch scheduled standard and steel. The pressure is 4.7 psig, and the temperature of the water is 60 degrees Fahrenheit. AFT Impulse can output forces and ballast from directly to Caesar 2. AFT Impulse does not consider 3D coordinates, and the reason for this is that the fluid, for the fluid, when you calculate the forces, the positive direction is the sense of the flow. So that will be the direction that it's going to be considered. So when it's exported to Caesar, it's only exported in the X. So you have to make the changes. Let's go back here. If you're to impulse, the positive sense will be here. So that would be it would be sent to Caesar in X, and you have to be careful and overwrite that and put Y direction, in this sense. If it gives you positive in this sense, it means it's negative for Caesar because Caesar has this direction, so it would be minus y. In this case, in the horizontal one, positive would be in this direction, so that would be minus c. So if you see minus c or plus c, then you have to change the cases created by impulse in Caesar when it is important to make to match the to put the correct sense of the forces in Caesar 2. So let's do a spectral analysis using Caesar. The first thing you have to do is generate the DLF curves. So to do that, you would go to AFT Impulse. You would go, when you're in the output, and you go to Export Force Files, and you select Caesar. When you select Caesar, then it will bring you up this menu. Since we're doing a spectral analysis, that means it's going to be applied at the same time, so you will select all the spectrums at the same time, not one at a time. Also, you have to send it in seconds, and always remember to include forces and include momentum and include friction. If you want to do it the traditional way, you would not do it, select one of these boxes, but as we saw, the results can be inaccurate, not only in the sense, but also in the magnitude. So once you do that, then you open Caesar, and you import the DLF curves into Caesar. To do that, you go to Tools, you go to External Interfaces, and you go to AFT Impulse. So this would be the Caesar manual. You would go to Interfaces, you would go to AFT Impulse. When you do that, then it brings you this window. So you select Browse, and you select the file that you created using Impulse. Here, it will ask you to say to specify the nodes that it's going to be applied. So here you have to put the Caesar nodes where the forces are going to be applied. In this case, it's going to be applied in the node 500 and then the node 300. So now it's going to warn you that the forces will be exported in the global X direction. So as I mentioned before, you have to correct this for the cases and all the spectrum that's created by Caesar, put it in the right directions that that Caesar is using. So once you import it, then you open dynamic. Input will be almost completed because the interface with Impulse will create all the cases for you, and it will create the force sets and cases as you will see. Forces directions need to be changed in force sets and load cases. So what we have here, this is automatically created by Caesar when you import it. So here's the DLF curve for node 500 and node 300. Frequency, forces, ling. This is created for you. Also, in the force sets, it's also created for you. The magnitude is also imported, but as I said, you have to correct this. Like in the horizontal, you have to put the Z direction, and in the vertical, you have to put the Y direction, which corresponds to node 300 and node 500. So now, let's go to the spectrum load cases. The spectrum load cases are created so you can combine them with the static load cases. So here it creates for you the first spectrum load cases using the DLF curve that is applied in node 500, which is in the horizontal. Factor 1, you leave it that way because it imports the real forces, but you have to be careful and change the Z. Here's the same thing. The second case is created for the vertical using the node 300 DLF curve. So now you have to specify y direction since it's in the vertical and the forces are applied upstream. So now all the combinations are created. As you know, spectral analysis does an independent analysis of the forces applied, or the set of forces applied. So it creates the program creates a first case which combines sustain with the dynamic load case 1, factor of 1 and 1. This is created for you. And you have a second case that is created, which is the dynamic load case and the sustain case. So now the only change you have to do in the spectral analysis, besides direction, also here when you get the control parameters, since it's a fast acting load, it is convenient to put a high frequency cutoff, because a fast acting load affects many frequencies. So now it's good for you to change to 100 the frequency cutoff. So that is the only change you need to make in the control parameters. So now you run the spectral cases, and what you get is, in the case 1, you have an overload of overstress of 37 pounds per square inch, and the allowable 30,000 pounds per square inch. That means it fails for 22%. So now let's see how you would do the time history analysis. Here you have to make a little bit of more work. The input required for time history analysis is almost exactly the same as that for spectral analysis. Both require the same force magnitude, direction, and location. Both will incorporate the same force time data. The fundamental difference in time history analysis is that data is applied directly to the model. It is time history is more realistic because it applies the forces as they happen in time, as a difference of a spectral analysis. In spectral analysis, instead converts the force time data into a maximum response curve with a maximum factor of 2, which is matched to the natural frequency of the system. Unlike spectral analysis, time history considers the time events and considers the kinetic energy of the system. So, as I said, time history is more precise, but not necessarily spectral analysis can be discarded, because it can be a very useful tool, as it has been for the last 20 years. As a difference from the spectral analysis, the input is not created automatically, so we have to manually input more data to perform this analysis. Time history analysis, as a difference of spectral analysis, shall be sent in milliseconds, and while spectral analysis requires seconds when importing from Impulse. So, generating the spectrums. Here, as a difference of spectrum, you have to create one by one. So what we suggest is, when you create it, and you export it, you create it with the node where it's going to be applied in Caesar. That way, it will be an excellent reference for you, and to remind you where it's going to be applied. So here, we're creating in the horizontal. And we give it a name as a node 500, since that is the corresponding node in Caesar applied. Remember, this is going to be applied in the Z direction. So now the second step is to create the second spectrum, which is going the one applied in the vertical section of the pipes, and this corresponds to node 300 in Caesar. So now you open dynamic input. you have to add 2 more pulse definitions in Caesar input. You have to create it. So we create force node 300. It's going to be time, force, linear, linear, and we create node 500, time, force, linear, linear. Once you do this, then you have to input the data. So you're going to add the data to the new pulses. So the first one we're going to add is the node 300. So now we come in here and we read from a file, and you would read from a file node 300 which you exported from Caesar. I'm going to go back a little bit to remind you. So this would be this one that you created for and you saved when you created the node. So here you would import from the file, and it would bring you all the information, the data that corresponds, that was created by Impulse, and it's imported, and you would get this table once you read from file. The second step is to do it for node 300. So the same procedure. You come in here, node 500, and you read from a file. You read from a file. You would read Spectral 900, and it would bring you the information that corresponds to that. So now the spectrums are created, and Caesar has all the information. So now you have to create the force sets. Location and direction. Magnitude is already defined in the spectrum when you import it. So here, careful with this. Do not put the magnitude that you read in Impulse. Just put minus the direction that it's going to apply it, and also put the correct direction Y and Z. Okay, so in 300 it would be, in this case, since it's in the vertical, it would be in Y, and -1 will say that the maximum load is applied in the minus direction. Why is in the minus direction? Because Impulse reports a positive force, which means the sense, and we saw that for Caesar that would be -Z, -Y. The same for Z. Impulse reports a positive direction because the force is applied in the sense of the flow. To Impulse is positive, so you would change it to the Z direction, and you would apply it in the minus direction. So you create these two cases applied in where it's going to, and you create the node force sets 1 and 2. Now you create the time history cases. So now you only create one time history case, and the reason for this is because time history applies them at the same time, different from spectra that it applies them independently. So you create node 300, node 500, factor 1. Again, pay attention to the direction, and you apply node 1, force set 1 and force set 2, which corresponds to the ones you created when you defined the force sets. The last step, the last step is create the static dynamic combination so you can examine according to code. So for that, you create one case that is sustained and dynamic, and it would be one dynamic case because you created give me 1 second, I'm going to go back to show you, because you created one time history. So it would be one case that you only need. The difference would be from spectrum, that spectrum you need to create as many cases as spectrum you hear and that you analyze. Here you only create one case. And the final step would be to update the control parameters in Caesar. Here, the same as on Spectral, you would change the frequency cutoff to 100 since it's a fast-acting load, and we said that it affects many frequencies at the same time. But also, it is good practice to change the time step. In this case, we use 5 milliseconds and duration 10 seconds because we took this information from Impulse. And really, I haven't proved whether or not this changed the results, but it seems reasonable to use the same time step and the same duration that Impulse uses, since it was original creating using that format. Once you finish this, then you run the time history analysis, and you see the results according to code. And what we get here is that there's a failure in the pipe of 36,800 pounds per square inch, which means it's 18%. It's, if we remember from Spectral, it predicted 22%. So you can conclude here that spectral analysis is more conservative, and that's why people is preferring to do time history analysis. So how do we prevent this failure from happening? The first option and the less expensive would be to close the valve slower. Initially, in the example, we closed it in 0.5 seconds. Here, you can close it in 1 second, and if you do so, you reduce the maximum stress to 30,000 pounds, which is 900 pounds below the allowable. Also, you can add, since you have high displacements in the horizontal due to the loads, you can add an actual restraint, and the equivalent load that you would need to absorb is 13,400 pounds. This, just to give you a reference, the civil engineers do not like loads above 3,000 pounds. So so this can be quite expensive, and the civil engineers would prefer you to find another solution, since they would have to make a lot of reinforcements, especially if it's in a pipe rack. Then they would have to add more braces. So they might not like this solution, and they maybe this would be a better solution for you. So a better idea is to try to lower the magnitude of the loads as possible, like we did using a valve, or you can use a surge tank is another solution you can think of. Conclusions. It is important to model Waterhammer events for proper system design and operation. AFT Impulse can generate transient forces which can easily be imported into Caesar 2 for either a spectrum or a history analysis. Traditional forces estimation techniques which rely on pressure difference can be highly inaccurate. And the manual method of the calculation of the force of rho times C times delta V times area can be too conservative, especially with partially closing valves, as we saw in the presentations that we did. Partially closed closure of the valve can also cause failure if not done properly. Like people tend to think that it's if you close the valve totally, the failure can occur due to Waterhammer was. And as we saw in the example, if you close partially a valve can also cause problems. Spectral analysis can be conservative compared to history analysis, and we saw the spectral analysis gave us a result of 22% of failure against 18% of history analysis. So with this we conclude. Do you have any questions? Well, thank you very much. If you think of a questions, just write to me, and I'll send you a response. Hopefully this webinar was of your interest. If you we invite you to join us to the future webinars, and again, thank you very much for attending. So what is next? You will receive an email with the link of the recorded webinar. You can see the presentation today. Also, you will be informed of the upcoming webinars. You can download a free demo on the website to to run some models. Also, you can run the ones that we have worked on today, or you can request an evaluation license. If you require pricing information, you can, if you're in United States, it's posted on a website. And if it's international, you can contact your local channel partners, see the website to see where your nearest channel partner is. Thank you very much again, and hope to see you in AFT next webinars.